Today we are going to continue with some other features of OpenCV that are usually used for image processing in machine vision applications. One of these features is increasing the size of the image while keeping the aspect ratio, decreasing it, and the images are called peer up and peer down, or going through the pyramid up and down, upsizing or downsizing the image by double its size while keeping the aspect ratio. Before the upsizing or downsizing of the image is performed, first Gaussian filter is used in order to blur the image, and then the image is zoomed in. So this is automatically implemented inside the function. This is a useful function and is a utility in some other algorithms that will be discussed in the following lectures, but we're going to mention it here because sometimes we're going to need to increase or reduce the size of the image. So we're going to use this image today, the logo, and in order to use pyramid up, let's do it. Result is to pyramid up from the source image. That's our image, and we have destination size. I'm going to take the shape of the image. It was just to check if I'm right. Okay, here's the shape. So I have 258, it's actually columns, and 195, so it's rows, columns, and the depth of the image. And now I'm going to go with twice the columns and twice the rows as a destination size, and visualize this. Visualize the result, and now we get twice the size of the image. It's the same image, but as you can see the dimensions are different. Or we can go with the other function. Maybe I should write in another result. So pyramid down, it will be the destination size, and pyramid down of the image. The result here will be 2 times smaller image. I'm going to load another image just to see what's going on. This image we have previously seen, and I'm going to perform this operation twice. So first I'm going to perform pyramid down of the image, then I'm going to perform pyramid up, and just to make sure, I'm going to take this shape again here after I load this image, so that we have the updated count, and then I'm going to visualize the result. So I'm going to have pyramid down of the image, then pyramid up again of the result, and show the result. Have a problem somewhere, so destination size is, let's go with the default. Here it is. I should also visualize the image below it so that you can see the difference. Here. So it's practically the same image, the same size. I have first used pyramid down and then pyramid out, which means that we have reduced the size of the image by double, and the pyramid down has made the transformation using the Gaussian blur function, first on the image and then reduced its size, and then we have made it in the other direction, pyramid up, which means we have doubled the size again. As you can see, we have a blurred result here of this image. The result after these two operations is a blurred image. This is something that it should be taken account when you're doing some image processing. Always keep the original image before you are performing some transformations, because by performing these transformations of scaling up, scaling down, or pyramid out, pyramid down, then you are losing some information, especially if you are going downwards. And also if you're doing pyramid up, you're not gaining additional information, which means the only information that you have are the ones that are already in the original image. I'm using this image just so you can notice the blur effect in the image when we have returned it to its original size. So pyramid down makes downsampling of the image, pyramid up makes upsampling of the image, and we get a result with the image that is twice the size by default or twice the reduced size by default. Another function that we are going to see, I'm going to use the logo again. Is the hue transform. For the hue transform, I'm going to need a grayscale image of the logo, and let's just print it out. So that we can visualize it. Okay, and hue transform is a transformation function that calculates the pixels in the image, makes a mathematical transformation of the pixels within the image, and this transform gives as a result the lines or the circles in the image. So what we have here is an image that is containing circles and lines, and hue transform will be used to extract the lines and the circles within the image. This transformation is good because it will give us the exact placement of the lines in or the images, and this is sometimes something that we need in order to perform this. So what we have is let's write the function first. Lines hue lines, and we have but first let's detect the edges before we use the lines. So we're going to use the canny edge detector. Is canny edge detector of our image. Let's use some threshold like, I don't know, 80, 100, and let's see the result first. It will get the pixels of the image and it will take the lines, and this out just to see if I have a good edge detection. Here it's good, it's a clear image. So now let's go with lines. Lines will take the result with this, and then we have the resolution as an input parameter. We're going to go with a 1. There is a resolution parameter for the degrees. So for each pixel we are searching now, 1 degree resolution we want in degrees. Then we want some threshold in which to detect a line. Let's go with the middle 128, and other parameters that are used, we're going to go for them with default values. Let's execute this. Okay, now we have the lines. I'm going to print out the line, and here we have the result of the lines. It is a vector that contains the lines, but it has calculated them with their polar coordinates. So we have the polar coordinates of the lines, and the polar coordinates are the radius and the degree from the center, which gives us that we have detected two lines with those polar coordinates. And if we want to visualize these lines, we're going to need to transform them again to Cartesian coordinates. For this, I'm going to use a predefined number of lines in Python. You can search them, you can Google them or find them. So this will basically transform the lines backward. We're not going to go into details about this. It's just the idea that is going to calculate the lines based on the lines that we have, and we're going to need an image where we're going to write the lines. Let's go with the regular image with white color. So here CV line is going to make a line between point 1 and point 2, so it's going to draw over that image, and then we're going to visualize that image again. The image is grayscale. I'm going to need the same image. Let's load it with full color, 3 channels, and write on over image 2. Yes, image 2. Okay, so over the logo we're going to write a line which will be, this is red probably, and visualize image 2. Let's see if this will work. So line is not blue, line of line. We're taking the coordinates inside line. Okay, this should work. We're going to need to import the package mat. For the calculation, okay, let's go back here. CV2, another error, IM2 is not defined. Okay, here we have IM2, this one needs to be recalculated, print the line again, and again this, so we have CV2. Here. Okay, and here we can see the two lines that it has found in the image, and we have drawn those lines. As we can see, we get the lines in polar coordinates, which means that we are aware that there is a line over there. We need additional post-processing to actually, if we want to get from where the line started until where it finished. So far it didn't get the horizontal lines. There is another function which could probably be used better. So this function is a probabilistic hue transform. So line P will be the result from it, CV2, hue lines P. This was just hue lines. We're going to use the same image as above, the resulting image, and again we have the resolutions. One, the degree, we are going with 1 degree resolution. Then we are having the threshold 128. Then we have additional parameters. It goes here none. Then minimum line length, let's go with 20, and gaps between the lines, let's go with, I don't know, 5, so we have a bigger degree of lines. Let's print out the results. Here we also have 2 lines, but now what we have is actually points of the lines. So we have origin point and destination point. So if we want to draw them in the image, we are going to go for in range 0 and of line P, and let's go with this and then draw the line over the image we were drawing over the res image. We have the line now, line 0 is the origin point, line 1, this is the origin point and the end point, line 2 with line 3. So we get these 4 points and we have 2 points. We need the color, let's go the other way around, and then some information about the line. And since we are drawing over the same image, we're drawing over image 2, let's execute this. I forgot. Okay, here it is. So we have the red lines here with the probabilistic approach. Depends on the application that you would like to use. Any of these would serve the purpose. So we can find the lines in the image and use this CV line to draw over them. It's a useful function sometimes because you can get the straight lines, and for some applications in image processing and machine vision you would need to get these lines. Another quite useful function would be hue circle transform, which, as its name says, will detect the circles in the image. So to detect the circles we are going to use hue circle. Circles will be hue circles. We need the image, so let's go with the grayscale now. That's IM. Method hue gradient. Then we go with the parameters are, the detection method is hue gradient. Then we need the inverse ratio of resolution, minimum distance between detected centers, then upper threshold of the candidate detector which is included in this function, the threshold for center detections. Let's go with default values for all the others, and let's draw the circles. We're going to use the function circle, which we'll use the result of the hue circle in order to draw the circle. So we are going to have more circles for let's go with 4 in range 0 length of circles. Let's just print out to check. I'm not sure how the output was of circles after it detects them. Hue circles, it's circles, sorry, here it is. It's still missing in position 3. Let's go with 1. Missing minimum distance, no default values, equals, let's go with 50. Okay, now it detected 1 circle. So what we have as a result for the circle is that we have the center of the circle and the radius of the circle. So inside the circle, let's go with this. There is only one, so I'm going to get the circle like this. Circle equals circles 0. Yeah, again 0. Okay. Okay, now we have the 3 points. I'm going to create a point. We need let's try like this. Invalid syntax. Okay, point is not defined. CV2 doesn't have numpy. Attribute error, has no point. Probably not. If there is no point, then we're going to just use a tuple. Okay. Here it is. It's rounded, and the radius should also be round of circle 2. Let's get them, yes, rounded values. And now we're going to draw the circle. Inside the image, drawing on image 2. Image 2, we have the center, we get the radius, and the color. Let's go with green. Don't think we have it. the types of lines that we are using inside the CV circle and visualize the image now again. I don't need this. Integer. I'm going to need to convert them to okay. Our argument became okay. Then I'm going to cast them one by one. So this one separately, this one separately. We have close bracket, so now we have a tuple, yes? Here it is. So here we have the circle. We did the thresholding to find the difference between circles that there is a minimum distance. Let me try with 0 here. Out of range 1. Okay, now it found more than one circle, which is obviously other circles that are over here, so we can place this in a for loop. Circles in range length of 0, and here we're going to have this inside. Let's this circle equals circles 0 A, and here the code will be the same. Then draw the circle, and in the end, after we finish this, visualize it. Error. Here it is, it drew all the circles. Let's go with something like this, so we have different colors. Here it is, as we can see, it found various circles. Inside it will also find the circle inside, so we place the threshold so we avoid concentric circles. Usually one circle would be enough if we detect it inside. If we need to detect them all, then we can just reduce the threshold. So practically what we have gone through in this class is getting the shape of the image, scaling up and down the image. Again, we are not adding with scale up additional information. We are actually losing information if we scale down and scale up again. And then we have gone to the hue lines, which transform the image in a way that allows us to detect the lines inside the image. So hue lines first requires edge detector prior to performing the line detection. There is a probabilistic implementation which detects the exact sets of points on the image, and we also have the hue circles, who has inside included canny edge detectors, so we can go with a grayscale image and detect the circles, and we can draw the circles with the function circle, draw the lines with the function line, which is already available and implemented in OpenCV.